All right, we're going to look at the distribution of the sample mean, and we're going to look at an example here where we roll a six-sided die. What is the mean and the standard deviation? Okay, so this is sort of elementary from considering what we've done before, but the mean, which I'll call mu, is going to be found by adding these values, possible values, and divided by the number. And that turns out to be 3.5. And the standard deviation can be found by using a calculator. And that's going to be around, let's just say squiggle 1.71. So let's, maybe around 1.7. So what can we think, how do we think of the standard deviation? Well, the standard deviation is going to tell us around what values we expect to get for rolling the die on average. Okay, so now let's call that A. B. Suppose we roll the die n equals 25 times. This is a sample. Okay, so this is a sample, and moreover, suppose a class of 20 students does the same thing. The same sample. Okay, so they're rolling the die 25 times. Okay, so here are some of the results. The thing is that I think that it's better to look at the type notes to see what those are, because it just takes such a long time to write those down. Maybe I can go really fast, but what I want to point out is that this is the result of people rolling the die 25 times. And what we can see is that these are not all the same numbers. And why is that? Because sometimes you're going to roll more and sometimes you're going to roll less. But on the other hand, we expect that we're going to get, on average, 3.5. And, well, these are pretty close to 3.5, but not exactly 3.5. Okay, so we're just going to roll through, we just do this, and if we take the average of these numbers, okay, so again, what is this? This is a class of 20 people, and they're all rolling the dice 25 times. So what we see is we can find the mean of these numbers. And the mean of these numbers is 3.518, which is about 3.5. So it's, it's what we'd expect, is that if we roll the die 25 times, we should get something that's close to this number up here. But one thing to notice is, how should we look at the standard deviation? If you take 3.5 and you add 1.7, you're going to get so you're going to get 5.2. If you subtract 1.7, you're going to get 1.8. Okay, so again, if you take this guy and subtract 1.7, you get 1.8. If you add 1.7, you get 5.2. but these guys, and that's adding and subtracting one standard deviation, 1.8 to 5.2. And the empirical rule says, well, that should be like around 68% of the time. But what we see is these are much more closer to around 3.5. So we would not think that the standard deviation is going to be 1.7, because this is not rolling the die one time, it's rolling the die 25 times and finding an average. So we see that the mean of rolling, the mean of a sample is a random variable. Sometimes the average is a little more of your sample, sometimes the average is a little less. So this is leading us to the central limit theorem. If a random sample of size n is taken, then the sample mean x bar is approximately normally distributed and the sample mean is exactly normally distributed if the population is normally distributed. The approximation of normal distribution works for any population when n is greater or equal to 30. Okay, so I don't know where they get those numbers. I mean, that's these are involved proofs, so we're not doing those proofs. Okay, the mean of the sample mean is called the standard error. And it is equal to the mean of the population. That is, mu x bar is equal to mu. So just as we saw before when we took the we had those 20 samples, people rolling the dice, that they rolled the dice 25 times, and we took the average, and we got something that's close to the average of our rolling the die once. So it's close to 3.5. But here's the thing which is sort of what that's what you'd expect anyway. But what's a little bit not so clear is this is what you get. The oh gosh, this is wrong. It's not the standard, which is called just forget this. The mean of the sample mean is equal to the mean of the population. So it's not the standard error is the next one. The standard deviation of the sample mean is called the standard error, written sigma x bar, and sigma x bar is equal to it's equal to the standard deviation of the population divided by the square root of n. All right, so that here there were roll the dice 25 times. The more you roll the dice, the larger n is, and the larger your standard deviation. Okay, so for our example, the population, which is one die, gives mu is equal to 3.5 and sigma is equal to 1.7. This is the mean and this is the standard deviation. When we roll the die n equals 25 times, the sample mean has mu x bar, so this is the mean of the sample mean. So it's a mouthful to say that. It's sometimes we say this, the expected value of the sample mean, so we don't have to do that. So it's mu, and that's 3.5. But sigma x bar, and this is the standard error, is going to equal sigma over square root of n, and this is 1.7 divided by the square root of 25, and that makes 1.7 divided by 5, and that gives 3.4. Sorry, equals 0.34. So note 3.5 minus 0.34 is equal to 3.16, and 3.5 plus 0.34 is equal to 3.84. How many of the sample means lie within 3.16 to 3.84? Let's just check that out to see whether this makes sense what I was talking about, see whether that was all nonsense. So if you go through these numbers over here, it was, well, it's a little bit hard to do this just so quickly, but 3.16 to 3.84, it's, you know, it's almost all of them. Well, not really almost all of them, it's a lot of them. This one's really low. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, I might have counted wrong, but anyway, I think that's 14. So the answer is 14 out of 20. This is 14 divided by 20, which is 70%. Recall that the empirical rule predicts 68% lie within one standard error. Here I'm using the word standard error instead of standard deviation. Standard deviation is for just rolling the die once, but standard error is rolling the die 25 times. But the thing is again, this number for the standard error is going to get smaller when the denominator gets bigger, when n is larger. And so what you're going to see is that this range, this is, so what am I doing here? I'm saying this is mu minus mu x bar minus sigma x bar, and this is mu x bar plus sigma x bar. This is one standard error of the mean, of the mean of the sample mean, the expected value, and we expect that you know, a lot of our population, 68%, will be in there if we have a normal distribution, and if this is the correct standard error, and that's what we found.